Good day, everyone. How fast are you moving with your studies in physics? There is an observation that the time is fast when we are busy with what we are supposed to do, but seems very slow when we are doing nothing. Hope you are doing the first and not wasting the time to study and learn. Like today, in our topic, make sure that you will complete the video lesson up to the end to acquire what you are supposed to learn from this topic. Today, the topic of this video lesson is kinematics, focused with equations of kinematics and how the quantities involved relate to each other, and how are these equations used in finding solutions to motion problems in physics. Kinematics is the branch of mechanics concerned with the motion of objects without reference to the forces which cause the motion. The kinematic equations are a set of 4 equations that can be utilized to predict unknown information about an object's motion if other information is known. The equations can be utilized for any motion that can be described as being either a constant velocity or a constant acceleration motion. On the road fronting this house is a car driven by a man not so old, with the distance traveled x and instantaneous velocities indicated. Notice that the distances covered by the car are equal, resulting to the same amount of instantaneous velocities, v sub 1 up to v sub 5. Calculating the change in velocity, delta v, which is v sub 2 minus v sub 1, the change in velocity is 0. By definition, acceleration is equal to the change in velocity in every unit of time. By formula, acceleration is delta v over t. With 0 change in velocity, the acceleration is 0. Describing the motion of a body with 0 acceleration. A body with 0 acceleration, the distance traveled 1 x sub 1 is equal to distance traveled 2 x sub 2 equal to distance traveled 3 x sub 3 and equal to distance traveled 4 x sub 4. The body has the same distance traveled in every unit of time. V sub 1 is equal to V sub 2 equal to V sub 3 equal to V sub 4 and equal to V sub 5. The body has the same instantaneous velocities. Because the instantaneous velocities are equal, the change in velocity is 0. The average velocity can be computed by dividing the total distance traveled by the total time of travel. The motion of the body is uniform. This car has increasing instantaneous velocities. The car has constant acceleration. A body with constant acceleration, to prove that the acceleration is constant, the change in velocities between 2 instantaneous velocities should be obtained. The change in velocity, delta v sub 1, 2, the difference between v sub 2 and v sub 1, the change in velocity, delta v sub 2, 3, the change in velocity from v sub 3 to v sub 4, the change in velocity from v sub 4 to v sub 5, when compared, are equal. The acceleration computed as change in velocity divided by time, that the acceleration A sub 1, acceleration A sub 2, acceleration A sub 3, and acceleration A sub 4, the value of the accelerations are the same. For a body with constant acceleration, the distance traveled in every unit of time changes, increasing or decreasing. The instantaneous velocities changes, increasing or decreasing. Has constant change in velocity, increasing or decreasing. The average velocity of the body can be computed by dividing the total distance traveled by the total time of travel. And it has a uniformly accelerated motion. When the instantaneous velocities increase constantly, the velocity and the acceleration are in the same directions. The acceleration is positive. But when the instantaneous velocities are decreasing at the same rate, the acceleration is negative. The directions of the velocity and acceleration are opposite. The body has a negative acceleration. With a constant change in velocity, the motion of the body is uniformly accelerated motion, UAM. This time, let's find the relationship between variables involved in a uniformly accelerated motion. The acceleration, distance traveled, velocity, and time. For a body with constant acceleration, how does the velocity vary with time? Using the definitions we had earlier for uniform motion and accelerated motion, average velocity and final velocity. Acceleration is defined as the change in velocity per unit time, or A equals delta V over T. And the change in velocity is the difference between final and initial velocities. Substitute, and the acceleration A is final velocity minus initial velocity divided by time. The final velocity then is equal to the sum of the initial velocity and the product of acceleration and time. Now, what is the body? What if the body started from rest? A body that started from rest has zero initial velocity. So what will happen to our equation? The final velocity is the product of acceleration and time. Taking the constant acceleration on the left side of the equation, the right side of the equation shows us the relationship between velocity and time. The velocity v is directly proportional to the time t. So how does the velocity vary with time? The velocity is directly proportional to the time of travel. This is known as the first equation of kinematics. For a body with constant acceleration, the velocity of the body is directly proportional to the time of its motion. The first equation is final velocity equals initial velocity plus the product of acceleration and time. The first equation of kinematics relates the velocity, acceleration, and time for v, a, t. In a motion problem, if two of these three quantities are known, the other quantity can be obtained using this equation. Now, What is the picture of the relationship between velocity and time? The graph of velocity versus time is a straight line graph sloping upward to the right. The slope of the graph line, which is the difference in velocities divided by the difference in time values in the graph, is constant and is equal to the acceleration of the body. Let's have an example. A car traveling at 10 meters per second accelerated uniformly by 1.5 meter per second square along a straight road. What is the car's velocity after 8 seconds? The given, the illustration, and the required are shown. The car's initial and final position at initial time t sub I equals 0 and t sub f equals 8 seconds. The initial velocity 10 meters per second and acceleration 1.5 meters per second squared, and the required, which is the final velocity of the car. The formula to use in solving for the required: the final velocity is equal to the initial velocity plus the product of acceleration and time. This is the first equation of kinematics. Substitute the given information to the working equation. 10 meters per second plus the product of 1.5 meters per second squared and 8 seconds. The final velocity is 22 meters per second. The final answer is final velocity equals 22 meters per second. What does this final velocity mean? It means that after increasing the velocity by 1.5 meters per second for every 1 second, from 10 meters per second, after 8 seconds, the velocity is 22 meters per second. Also, the acceleration is positive, 1.5 meters per second squared. The final velocity should be greater than the initial velocity. 22 meters per second is greater than 10 meters per second. For a body with constant acceleration, how do the distance traveled and the time of travel vary with each other? Acceleration is equal to the change in velocity divided by change in time. The first equation of kinematics: final velocity equals initial velocity plus the product of acceleration and time. From the definition of average velocity, bar v is equal to x sub t divided by t sub t, and average velocity is the sum of the final velocity and the initial velocity divided by 2. Average velocity is equal to average velocity. This is the identity equation. The ratio of distance traveled and time of travel is equal to the sum of final velocity and the initial velocity divided by 2. Cross multiply. Substitute v sub I plus a times t for the final velocity. Distribute the time t. Add initial velocity times time, v sub I times t plus v sub I times t. Then divide both sides by 2. The distance traveled by x is the sum of the product of initial velocity times time and 1/2 of the product of acceleration and the square of time. This is the second equation of kinematics. For a body that started from rest, the initial velocity is 0. The distance traveled x equals 1/2 a times t squared. This equation relates time acceleration, and distance traveled. T, A, X. The constant of proportionality between distance traveled and time, 1/2 A, is equal to X over T squared. It shows the relationship between distance traveled and time, that the distance traveled is directly proportional to the square of time. For a body with constant acceleration, the distance traveled by a body with constant acceleration is directly proportional to the square of time. The graph of relationship between distance traveled and time of travel is a parabola that opens upward, suggesting a direct square proportion between these variables. How about the graph between the distance traveled and the square of time? The graph of distance traveled x and the square of time t square is a straight line graph sloping upward to the right, suggesting a direct proportion between distance traveled and square of time. The slope of the graph line of the distance and the square of time is equal to 1/2 of the acceleration. So what does the second equation of kinematics tells us about the relationship between distance traveled and time? The distance traveled by a body with constant acceleration is directly proportional to the square of time. Example: a car traveling at 10 meters per second accelerated uniformly by 1.5 meters per second squared along a straight road. What is the distance traveled by the car after 8 seconds? The given illustration and the required. The illustration includes the initial velocity, the time elapsed, and the acceleration of the car. The length of the final position of the car from its initial position is the required in the problem. The formula to solve the problems: the second equation of kinematics. Distance traveled equals the sum of the product of initial velocity and time and the product of 1/2 acceleration and the square of time. Substitute and calculate the given velocity, time, and acceleration. When substituted to the equation, the distance traveled is equal to the sum of 80 meters and 48 meters. The distance traveled is equal to 128 meters. Don't forget to write the final answer. The distance traveled is equal to 128 meters. How about the relationship between the velocity and distance traveled? How will you calculate either the velocity or the displacement when the time of travel is not provided? For a body with constant acceleration, how do the velocity and distance travel vary with each other? Let's derive the relationship between these variables. Acceleration is equal to the change in velocity divided by change in time. The first equation of kinematics. Final velocity is equal to the initial velocity plus the product of acceleration and time. Average velocity is equal to the ratio of total distance and total time. And average velocity is the sum of final and initial velocities divided by 2. The first equation of kinematics can be expressed as time t equals final velocity minus initial velocity divided by the acceleration. And this equation of average velocity can be stated as time t equals the ratio of distance traveled and average velocity. Identity equation: time equals time. Substitute v sub f plus v sub I for average velocity. The difference in velocities divided by the acceleration is equal to the ratio of the distance traveled and the sum of the velocities divided by 2. Cross multiply. 2ax is equal to the product of the sum and the difference of final and initial velocities. The special product gives us the product of the sum and the difference of two the same numbers is the difference of two squares. From these equations, the displacement x is equal to the ratio of the difference of the squares of final velocity and initial velocity and twice of the acceleration. And the square of final velocity is equal to the sum of the square of initial velocity and twice of the product of acceleration and distance traveled. These are the third equations of kinematics. How do the distance traveled x and velocity vary with each other? This third equation is equal to the ratio of the difference of the squares of final velocity and initial velocity, and twice the acceleration. If the body started from rest, initial velocity is 0. The equation becomes displacement x is equal to the square of final velocity divided by twice of the acceleration. Taking the constant of proportionality on one side of the equation, 1 over 2a equals x over v sub f squared. The third equation of kinematics relates the velocity, acceleration, and distance traveled. V, A, x. The equation shows that the distance traveled x is directly proportional to the square of velocity. So how is the distance traveled related to the velocity of the body? For a body with constant acceleration, the distance traveled by the body is directly proportional to the square of its velocity. The graph of distance traveled and the square of velocity is a straight line graph sloping upward to the right. The slope of the graph line is constant, and the slope is equal to 1/2 of the acceleration of the body. The other statement of the third equation of kinematics, final velocity is equal to the sum of the square of initial velocity and twice the product of acceleration and distance traveled. If the body started from rest, the initial velocity is 0. The equation becomes final velocity square is equal to twice of the product of acceleration and distance traveled. The constant of proportionality 2a is equal to the square of velocity divided by the distance traveled. It relates the velocity, acceleration, and distance traveled. VAX. So what's the third equation says about the relationship between velocity and distance traveled? For a body with constant acceleration, the velocity of the body is directly proportional to the square root of its distance traveled. How does the graph of velocity and the square root of distance traveled looks like? The graph of velocity versus the square root of distance traveled is a straight line graph sloping upward to the right. It suggests a directly proportional relationship. The slope of the graph line is constant, and the slope is equal to twice of the acceleration of the body. If you want to have a more detailed discussion on graphs and relationships, there is a video lesson about that in this channel. Let's consider this motion problem as example. A car traveling at 10 meters per second accelerated uniformly by 1.5 meters per second squared along a straight road. What is the distance traveled by the car when its velocity reached 25 meters per second? The given illustration and required. The illustration shows the initial and final velocities and the acceleration of the body. The formula or working equation to solve for the required is distance traveled S is equal to the ratio of the difference of the squares of velocities and twice of the acceleration. Substitution and calculation. Substituting the values of final velocity, initial velocity, and the acceleration. The distance traveled is 175 meters. The final answer is the distance traveled x is equal to 175 meters. Another motion problem to apply the equations of kinematics. In a 500-meter car race, car A and car B started from the same starting point with car A ahead of car B by 2 seconds. Both cars accelerated uniformly up to the finish line. The acceleration of car A is 3 meters per second squared. What is the acceleration of car B if they reach the finish line at the same time? What is the speed of each car at the finish line? The given, illustration, and the required. The illustration shows the positions of the cars from the start to finish, the magnitudes of acceleration, and the distance traveled. Notice that the distance traveled by the two cars are the same. The time of travel of car A is greater than that of car B by 2 seconds. The formula to use in problem solving. For letter A, acceleration of car B is equal to twice of the distance traveled by car B divided by the square of time of car B. This equation was derived from the second equation of kinematics. The time of travel of car B is equal to the time of travel of car A minus 2 seconds. To solve for the time for car A, time sub A is equal to the square root of twice of distance traveled by car A divided by the acceleration of car A. How is this equation obtained? From the second equation of kinematics, this equation was derived. The square of final velocity of car A is equal to the twice of the product of the acceleration of car A and the distance traveled of car A. The same formula will be used to determine the final velocity of car B. Substitution and calculation. Solving for the first required. The time taken by car A to reach the finish line is the square root of 2 times 500 meters divided by 3 meters per second squared. The time is 18.26 seconds. The time taken by car B to cover the same distance is 18.26 seconds minus 2 seconds. Time sub B is 16.26 seconds. The acceleration of car B is 2 times 500 meters divided by the square of 16.26 seconds. When calculated, The acceleration of car B is 3.78 meters per second squared. The answer may be checked by comparing the distance traveled by the two cars. Distance traveled by car A is equal to the sum of the product of initial velocity and time and half of the product of acceleration and the square of time. And for car B, for car A, 500 meters, and for car B, 500 meters. The distance traveled by the two cars are the same, suggesting that the computed acceleration of car B is correct. How about the velocity of the two cars upon hitting the finish line? The final velocity of car A is 2 times 3 meters per second squared times 500 meters. The final velocity of car A is equal to the square root of 3,000 meters square per second square. And the final velocity of car A is 54.77 meters per second. For car B, the final velocity is the product of two 3.78 meters per second squared and 500 meters. Square root of 3,780 meters square per second square. The final velocity of the car is 61.48 meters per second. The final answers are: the acceleration of car B is 3.78 meters per second squared. The final velocity of car A is 54.77 meters per second. And the final velocity of car B is 61.48 meters per second. The fifth example. A car is at the stoplight approaching a straight road. When the green light flashed, a motorcycle passed the car with a speed of 20 meters per second. At that instant, the car started moving with an acceleration of 2 meters per second squared. How long will it take the car to overtake the motorcycle? How far from the stoplight will the car overtake the motorcycle? What is the speed of the car when it overtakes the motorcycle? The given, the illustration, and the required. The position of the car and the motorcycle, initial velocity of the motorcycle, initial velocity of the car, and its acceleration, and the unknown information, time of travel of the car, and the distance traveled by the car and motorcycle are provided in the diagram. To solve the problem, the formula are: time of the car to overtake the motorcycle is equal to the time of travel of the motorcycle and can be represented by T. Distance traveled by the two vehicles are equal. The time of travel of the car can be expressed as the ratio of twice of the average velocity of the motorcycle and the acceleration of the car. How is this equation obtained? From the equality of distance traveled, this equation of time was obtained. For letter B, the distance traveled by the car can be obtained using the second equation of kinematics. And letter C can be answered using the first equation of kinematics. Substitution and calculation. The time taken by the car is twice of 20 meters per second divided by 2 meters per second squared. The time taken by the car to overtake the motorcycle is 20 seconds. The distance traveled by the car before overtaking the motorcycle is 1/2 of the product of 2 meters per second squared and the square of 20 seconds. And the distance traveled is 400 meters. To check if this is correct, this distance should be equal to the distance traveled by the motorcycle, which is the average velocity times time. 20 meters per second times 20 seconds is equal to 400 meters. The distance traveled by the car is equal to the distance traveled by the motorcycle. The last required is the final velocity of the car when it overtakes the motorcycle. Substitution and calculation. The velocity of the car is 2 meters per second squared times 20 seconds. And the velocity of the car is 40 meters per second. The car's speed is much greater than the speed of the motorcycle when it passed the motorcycle. The final answers to this problem, based on the required, are: A. Time for the car is 20 seconds. B. The distance traveled is 400 meters. And C. The velocity of the car is 40 meters per second. That completes the discussion on this topic, Equations of Kinematics. This topic discussed the motion of the body with zero or constant acceleration, accelerating positively or negatively. Let's test your understanding from this lesson. Try to solve these problems completely on a piece of paper. When done, have your solutions checked by your instructor or professor. For problem number 1, the car is traveling at 36 kilometers per hour when the driver decided to accelerate at a constant rate for 20 seconds. How many meters was traveled by the car when the driver viewed the speedometer with a reading of 108 kilometers per hour? And for problem number 2, cheetah is the fastest moving land animal on Earth with a maximum speed of 33.5 meters per second in short distances. And it can accelerate from rest to 16.7 meters per second in a matter of 3 seconds. A cheetah at rest started chasing a deer 200 meters away, moving with a constant speed of 20 meters per second in the same direction. How long did it take for the cheetah before it possibly caught the deer? Hope you have acquired what you are supposed to learn from this topic. If you learned from this video lesson and believe that other students will also learn from this presentation, like and share this video. If you want to watch more physics videos and learn more through video presentations, it's time for you to subscribe to this channel, so you will be alerted for new videos coming. Learning physics should be enjoyable. Video lessons here can do that for you. Thanks for watching. God bless, stay safe, and good luck.